Greetings, welcome to the course on Operations Research Technique. We are right now in Unit 1, Linear Programming Problems. In that we have seen how to formulate the model, mathematical model from given data, and we also saw and discussed graphical method of finding solution to linear programming problem. And we have seen limitation of graphical solution. Graphical solution method can be applied if and only if there are two variables in that particular problem. If any problem, linear programming problem, is having more than two variables, then we cannot use graphical method, because we know that restrictions on graph is it is 2D. So we will have only x-axis and y-axis. So either we will be selecting two variable, one on x1 axis and other on x2 axis. But if we are having in real life more than two variable problem, then definitely graphical method fails and we have to go for analytical method. And the analytical method used in linear programming problem is referred as Simplex method. The name is Simplex method, which is mathematical method in tabular form, and other name of Simplex method is Big M method. So Big M means capital letter symbol M from the alphabet, and therefore since it is in large cap, so we are referring that method as Big M method. Now one thing you have to keep in mind, Simplex method can be used for two variable problem as well as three variable problem. It is not that only we can use it only for more than two variable problem. So choice is ours whether we have to use two variable problem or more than two variable problem, which particular method, Simplex or graphical. So by default, if it is to be solved by graphical, no option other than for two variable problem to choose graphical method. But if problem is either two variable problem or more than two variable problem in decision making, we can go for any of the method for two variable. But for more than two, I am repeatedly saying, for more than two variable only mathematical, that is Simplex method. Suppose I am having now two variable problem, choice is given to me, find the solution of this particular problem. So what I will do, I will opt easiest way for two variable problem, graphical method. Two variable problem can also be solved by Simplex method also. Today we will see in detail how to proceed, how to solve step by step linear programming problem by Simplex method. So let's start. Now here you can see and we have discussed many times, most real life problems, the problems which we are coming across in day-to-day cases are, when formulated as an LP model, have this is very important, have more than two variables, and therefore need a more efficient method to suggest optimal solution for such problems. We shall discuss now a procedure called Simplex method for solving LP model of such problem. This method, as already explained, was developed by Danzig in 1947. So now we will go to details of this particular method. So for your reference, I have given various steps in details. before that I want to explain something more. Now here you can see the use of simplex method to solve LP problem requires that the problem is converted into its standard form. Problem is to be converted into its standard form, that is the requirement. Into standard form. So now let us check what do you mean by the problem is to be converted into standard form. If you recall, we have written in earlier cases equations like, say, maximize z equal to x1 plus 2x2. For example, I am hypothetically writing x1 plus x2 less than equal to 5x1 plus 3x2 suppose less than equal to 10 and x1 x2 greater than equal to 0. Focus your attention now on what I have written. Here this formulation which I have written in this corner is nothing but it is formulated version from the given data. LP formulation, this is in the form of linear programming formulation for maximization type of objective function. Now whatever initial formulation we are doing based on what? Given data, either in the form of this is very important, either in the form of less than, greater than or equal to constraint is called as canonical form. What I am saying, the formulation which we are doing from the given data for finding solution is referred as in canonical form. We have to convert that into standard form. Now what is the meaning of this standard form is, if you are having this equation, you have to convert this into equal to. If I am having other equation, I have to convert this equation also into equal to. And interestingly, if I am having equal to in canonical form, I have to again convert this into equal to for standard form. Means what I am saying, in standard form I want all constraints in equal to form. I want all constraint in equal to form. How we can do that? How we can proceed for that? Suppose this is the given condition. Here it is written x1 and x2 greater than equal to 0. The beauty of linear programming as a tool in operations research for decision making is that it talks of reality, possible results which you are likely to get. The meaning of this my sentence is, when I am saying it talks of reality, what assumption we are quoting here? x1 and x2 greater than equal to 0. Suppose a person who is running any business and decides to produce some units of x1 and x2. As stated in the condition, x1 and x2 has to be greater than equal to 0. Now assume, students, what worst can happen with that businessman? At the most, the quantity of units of products which he is assuming to for production, say x1 and x2, at the most will be equal to 0. He cannot produce negative quantity of x1 and x2. This is very important, and therefore I am saying it is taking care of reality. Reality, 0 is possible, no production is possible, but producing something negative quantity, -5 chair, -5 car, -10 scooters, that is never possible. If things go worst against that particular decision maker, the decision variable at the most can have value equal to 0. Or if things are within control, he will have values more than 0. This is one point. And now this simplex algorithm which we are discussing is a step-by-step process. The meaning of step-by-step process is we are starting from scratch. When I am supposed to find the values of x1 and x2, I will start from very scratch, and scratch is x1 and x2 equal to 0. It cannot be negative, that is very important. x1 and x2 maximum can be 0. So in linear programming, what we do in simplex, we start from base, that let quantities to be produced are 0, and then we go by improvising step by step, and at one particular point we reach where our solution is optimal solution. So initially values of decision variables to start will be at 0 level. If there are 10 decision variables like x1, x2, x3, x4, x5, x6, x7, x8, x9, x10, very first algorithm, mind well, remember this thing, very first algorithm, when you start writing first simplex table, all these decision variable from x1 to x2 will have value 0. We'll start from that 0 value of all these decision variable, and step by step we'll improve. Got it? And we will terminate our algorithm, simplex algorithm, at a point where further improvement is not possible. That particular point will be terminating simplex algorithm. Else it will continuously improving the solution starting from scratch, that is decision variable 0. I am giving emphasis to this concept because of only this criteria convert into standard form. If we did this aspect carefully, further things are little bit simpler. Now how to convert this? Suppose greater than equal to less than equal to equal to. See here, I think you can see this, x1 plus x2 less than equal to 5. If I assume initial values of x1 and x2 as 0, so this will be 0 less than equal to 5. 0 less than equal to 5 is not possible. So to compensate that, what we have to do? For this equation we have to add slack means this equation will become x1 plus x2 plus s1 is equal to 5. This is what converting this equation into standard form. I have converted this less than equal to sign into equal to sign, and I have introduced slack variable. Here left side is having less than right side. Less means in English deficit. Other meaning of deficit is slack. So add slack to compensate left hand side and right hand side. So it becomes left hand side original value plus slack is equal to now right side value. Similarly, second equation will be 5x1 plus 3x2. What I shall write now? Guess. Deficit, slack. There is some deficit in left side. To compensate that and to make it equal to right side, we have to add something. And what we have to add? Add amount equal to deficit, and deficit is called as slack. So we will be adding again slack s. I am using this second time, so I have taken suffix as 2, and here it will be 10. Mind well, I am not interested in values of this s1 and s2. I am only interested in values of x1 and x2. Now in standard form, for this case the objective function will change. It will be maximize z x1 plus 2x2. Now you have introduced intentionally these two variables, so there will be their profit coefficient as 0s1 plus 0s2. This we will study in next slide in detail, only to give you understanding of conversion of given data into standard form. I have explained through this example. If it is having equal to sign, here we will see how to treat this equal to sign. Suppose the equation is x1 plus x2 equal to 5. If this is the problem, original problem. Now if I put this condition as 0, so this will lead to 0 is equal to 5. And mathematically this is wrong. 0 is not equal to 5. To compensate this, whenever there is in original canonical form we are having equal to sign, what we are doing? x1 plus x2 plus a is artificial variable now. To compensate this error and equal to 5. So we have seen for less than equal to you have to add slack, for equal to you have to add artificial. Now let us take the example of, we'll drop this. I will now explain for, suppose the sign is (3x1) plus 2x2 greater than equal to 10. This is the equation we are having. Again, if we put this basic condition of 0, so this will lead to 0 plus 0 greater than equal to 10. Again, this is not possible. And here we can see that this particular side, left side, is having surplus than right side. This is the sign greater than equal to. Greater than equal to is only possible when this amount is surplus than this amount. So to compensate this, what we have to do? We have to subtract surplus amount. So analogous will be 3x1 plus 2x2 minus s1 surplus. This s stands for slack, this s stands for surplus, since it is greater than equal to. And suppose I write equal to 10, and by putting this condition, what I am getting? Minus s1 is equal to 10, s1 is equal to minus 10. Again this is violating the basics of linear programming. Let it be your real variable, let it be your fictitious variable, which are introduced in the problem. In OR, all are either equal to 0 or greater than equal to 0. No negative sign is permitted for any real or fictitious variable. At the most, it will have 0 value, or value will be greater than 0. No negative. Now here we can see, if we treat like this, what we are getting? S1 equal to minus 10. So this is wrong by the concept of operations research. To compensate this, what we are doing now? In this case, to compensate for this negative sign, what we have to do here? We have to 3x1 plus 2x2 minus s1 plus a1 equal to 10. Now this is perfect standard form of given case. So what we have seen right now is how to convert given canonical form into standard form. This is one aspect. Now I took maximum time for this particular case. Now importantly, what are the other requirements when we want to solve that problem by simplex method? First, all constraints should be expressed as equations that we have seen by adding slack, surplus and artificial variables that I have explained. Right hand side of each constraint should be made non-negative. The meaning of this is, suppose I am having 3x1 plus 2x2 less than equal to minus 5. So this is negative. What is given? Right hand side of each constraint should be non-negative. So I have to convert this minus 5 into non-negative value. If not, naturally, normally we will have these values positive. But if it happens to be negative value, then this is done by multiplying both sides of the resulting constraint by minus 1. So how I will convert this into right side? I have to multiply both sides by minus 1. So it will be minus 3x1 minus 2x2. Now when you multiply by minus sign, inequality sign will change. So it will be minus 3x1 minus 2x2 greater than equal to, very important, greater than equal to 5. So this is second, and objective function should be maximized. Now the condition is given because we are going for one method wherein we are interested to solve problem by or in the category of maximization. We can definitely solve the same problem by the logic of minimization. But for better understanding and to avoid confusion, one method is understood which will be for maximization. So what we have to do, initial change in minimization problem and then solve it by maximization logic, interpret answer in the form of minimization. So you are not required to recall or remember separate steps for minimization and maximization. How you will convert minimize to maximize? It's very simple. Suppose the objective function is minimum z equal to 3x1 plus 5x2, and if I want to convert that minimum to maximum, only I have to multiply right side values by negative sign, that's all. So that is given. The objective function should be maximization. If it is in this form, what is written? Maximize to minimize. What is the change? Here you can see Cj minus Xj. Here what is done is multiplication by minus sign. I think it is clear. Now this table we will be concentrating on, suppose you focus your attention on this part, because in previous we have written that we will be studying procedure for maximization. Means what I will be interested in converting minimization to maximization. Even I can go for specifically minimization. Right now we will see how it will work. In previous slides and previous discussion we have seen how you are adding, when you are adding slack variable, when you are adding artificial variable, when you are subtracting surplus variable and adding artificial variable, 3 cases. So we have seen for this case what we have discussed, add slack in last slide. For this we have seen subtract surplus and add slack artificial and equal to, we have seen we have to add artificial variable. Now what is given here, if it is less than or equal to, if it is this sign, a slack variable is added, this is given. Coefficient of this variable in objective function for maximize will be 0. Why 0? Because it is fictitious one. When we are not producing any amount of slack variable, so naturally there won't be any profit contribution from slack variable, and therefore we have to put multiplying coefficient of those variable for objective function as 0. For minimize it is 0, and presence of additional variable in initial solution, yes. So initial solution will be represented for this equal to by slack variable, and here I will interpret that slack variable as S. Second case, greater than or equal to, now coefficient for surplus will be 0 and for artificial it will be minus m. But what is given? Will it be surplus variable representing solution? No. Yes, artificial variable will represent solution if it is greater than equal to. Third case, of equal to, only artificial variable is added. For objective function, coefficient is minus m, and if this is the case, your initial solution will be artificial variable. So how you have to remember? Simple logic. For less than equal to, current initial solution variable is slack variable, that is S. For greater than equal to, you will be subtracting S surplus, adding artificial A, and initial solution will be artificial variable. When it is equal to case, in original formulation, you are adding artificial variable and your solution, initial solution will be represented by artificial variable for that constraint. I think, is it clear now? Things will be more clear when we will be solving problems based on this logic. Let's move ahead. These are the steps which I have already explained. Formulation simplex algorithm. Now see here, this is for, all these steps are for maximization case. Means if problem is minimization case, we'll convert that minimization case problem first into maximization case, then we'll follow these steps. How to convert minimize to maximize, that we have seen. One more condition, if you forget, right side of the equation, that is resource value, constant right side value has to be positive, non-negative. If it is negative, multiply entire equation by minus sign. Do not forget to change inequality sign. While multiplying, if it is less than equal to, you have to convert it into greater than equal to, and vice versa. First thing, formulation of the mathematical model, we have seen many times, we have practiced this. This is discussed just now, many times I have discussed how to convert. And non-negativity, check all BI, that is row source value, are positive. No right side negative value is allowed or permitted. Then express given LP model as standard form by adding additional variables in constraints. Step 2. What is that? Set up initial solution. Write down the coefficient for variables of the LP problem in tabular form as shown in the table. I will show in next slide. And get initial feasible solution. So it starts from scratch, that is assuming, for this step, assuming all x1, x2, xn equal to 0 in first step. This is very important. All decision variables are assumed to be 0 in first step, and then we'll progressively move ahead. Now, can you see this table now? This simplex table, which is indicating you all variables which we have listed in formulated version. We have seen mathematical models as a formulated version from the given data. All those data is then represented in the form of simplex table. This table is called as simplex table. See here, one is this part, other is this part. Extreme half of this table, which talks of variables, actual variables, which are into the problem during formulation, which we have assumed let x1, x2, x3, xn be the units of particular things being produced. And these S1, S2 or A1, these are added when we have converted this form into standard form. And this table, simplex table, we are writing after converting into standard form. Once we have converted given canonical form into standard form, then only we are writing this particular table. Now I will explain this table. This part of real variable is called as body part of this matrix. This other than the real variables, this part is referred as identity part of the matrix. Body part, identity part. This is body part, this right side is identity part. And we will see in problem how to fill these values. What is the meaning of all these, that we will understand. For the time being, body part, identity part. Identity, you can see identity is written 1 0 0 like that, 0 1 0 0 1 like that. That is about right side. Now here you can see this column of basic variables, which is represented by B. So these are the variables in the current solution, the solution which we are trying to optimize, whether it is, we are finding whether that solution is optimal or not. For that, whatever values we are getting are written in this column of basic variable. Basic variable value means whatever we are getting out of that basic variable is we are writing its value. Solution which we are getting by putting the initial conditions, and these variables representing that initial condition, those values we are writing here. This is very important. This row is called as profit contribution per unit, contribution per unit. So this is written from the objective function equation from standard form. These values C1, C2, C3, Cn values are the profit or cost values of the decision variables from objective function that we will be writing here. And here you can see this column, basic variables coefficient. So here we are writing for all the values. Here amongst these variables, some variable will be representing solution. Amongst these large number of variables, some variables will represent the solution, and for those variables which are representing solution, we will be writing their Cj value, but will be called as basic variables coefficient. These values are same as that of Cj value. So suppose for x2 I am having C2 value, and if x2 is coming over here, the value will be C2, real value which happens to be there in the problem. Got it? Now, and these are all calculations. This is deciding row. This Cj minus Zj row will decide the fate of this particular problem, whether final solution is achieved or there is yet some scope for improvement of the solution. And as you know, we are finding these values for maximization type of problem. There is one condition for this Cj minus Zj. Here it is given where Cj minus Zj net effect incoming profit per unit minus Zg outgoing total profit cost. If this value, there is condition for maximization type of problem, if we satisfy by getting this Cj minus Zj value as per the criteria, we say solution is optimal, else we say there is scope for improvement. That we will discuss. Now, test for optimality. That what I have just now said we will discuss. We have seen our focus, our intention will be now on Cj minus Zj row values. Our interest will be on Cj minus Zj row values. What the condition says. And we are talking of again I am writing for objective function maximization. We are talking for objective function maximization. For maximization case, for solution to be optimal, remember, if all Cj minus Zj are greater than equal to 0, then the basic feasible solution is optimal. If at least one Cj minus Zj is greater than 0 and each of these columns have at least one positive element for some row, then this indicates that improvement is possible. The meaning of this statement is, whenever I am calculating all Cj minus Z0 values for maximization type of problem, all values must be 0 or negative. What is written? Less than equal to 0. Less than equal to is what? Negative. Less than equal to is negative. If in that entire row of Zj, Cj minus Zj, any single value if happens to be negative, positive, again that problem will be going into the loop and you have to solve it for next iteration, and this iterative procedure you have to continue. Now once the problem has entered into the loop, you will continue the same process till this condition is satisfied. The moment this condition is satisfied, algorithm terminates. There are computer programs also available which takes care of large complicated interrelated decision variable, and the algorithm terminates when this condition is checked and found to be satisfactory. Next, once you find that solution is optimal, you will stop, problem is over. But if by chance it happens to be further improvement is possible, then you have to go for step number 4, and the step number 4 is select the variable that enter the basic. Means now you are in that solution, you will be having some decision variable which are not satisfying that condition. Now you have to reshuffle your solution such that Cj minus Zj condition is satisfied. That is given. How to check is given here. We will implement this method when we go for numerical. Now when I say that improvement is possible, these are the detailed steps I have given for you. Definitely you can read the contents which is mentioned on the slide. Once you decide that your solution is not optimal solution, for improvising you have to find the variable which is likely to come into the picture and the variable which is likely to leave the solution. So these two aspects are important, that is entering variable and leaving variable. So it is talking of that part where the variable will leave the solution. Again this we will discuss in problem. Just remember the steps. I will directly implement whatever I have written here. This is for you people to give detailed aspect of what is the meaning of this particular heading. And now once we have decided that okay, initial solution was not optimal and we are moving ahead and we have decided entering variable, outgoing variable, I have to check now for new solution. This formula, this particular formula we will be using in analytical treatment, this formula. I will explain this in very simple way when we solve numerical. Again I am repeatedly saying this entire slide is giving you details of the related steps. So you should not miss, when you study you should not miss any of the concept. Therefore these are the detailed slides given. And once we find this, as I said, you will be going in do loop like situation. Things will repeat. Only algorithm will terminate at the point where other condition, last condition, that is Cj minus Zj row value, deciding row value, if all values are either 0 or negative, then only we will say solution, final optimal solution is achieved for minimization case. Else to that point we have to repeat the procedure. You can find this problem. So this is the problem, and here it is written, use simplex method to solve the following linear programming problem. Now here you will be surprised. If you meticulously look to the problem, you will be surprised. Why I am saying like that? Somebody will say, sir, there are how you directly say solve it by simplex method? Cannot we solve this particular problem by graphical method? Think for a while. Can I solve this problem by graphical method? Obviously, your answer should be no. Why? It's very simple. Here you are using 3 variables, x1, x2, x3. Students get confused. Here they find only x1, x2. Here they find x2, x3. Okay, and here they find 3 variables. So there is a lot of confusion. Sir, somewhere here it is given 2 variables, somewhere it is given 3 variables, like that. Mind well, students, you have to identify total variables given in that particular problem. Total variable, total real variable. If total real variable are 2, then use graphical or simplex, choice is yours. But if 3, no choice with you, only you have to go for graphical. In next lecture, we will be covering details of simplex method. We will be applying all the steps. We will be applying all the steps which we have discussed in today's lecture for finding solution to this problem which is stated on the board. Till then, study all the steps given, discuss, implement, try to implement how you can convert equation into equation less than equal to sign, greater than equal to sign, or equal to sign. With sufficient practice, you will get confidence. With that confidence, we will go in the next lecture to find solution of a given maybe 2 variable problem, maybe more than 2 variable problem by simplex method. So here today we will stop, and we will be covering analytical solution, real application of the problem from next lecture by this particular example.